So section 8.2 is going to talk about the area of a surface of revolution. So what's going on is you're going to be taking a curve and rotating it around an axis and then asking, all right, well, what's the surface area? So for example, something like this pictured in our book, you take this curve, you rotate it around an axis, you get a volume. And we calculated the volume in chapter 6, but now we want to find the surface area. We're actually, as our last problem, going to go back and take a look at the kind of peculiar thing that's happening between surface area and volume for one particular problem called Gabriel's horn. Now here's all the formulas you're going to need for this section. If you have a function of x and you're rotating around the x-axis, then this is the formula that you're going to need for finding its surface area. If you're rotating about the y-axis, the big difference between these two formulas, in fact, the only difference, is you're going to place the f of x by just an x. And let me zoom out a little bit. Sorry, I didn't realize I was still zoomed in. So this is if you're rotating around the x-axis. This is if you're rotating around the y-axis. You could also have a function that's x defined as some function of y. And if that's true, that's fine. Here's the formula for finding the surface area rotated around the y-axis. And I'm not going to hit you up with rotating around the x-axis. We could do that, but this is plenty of formulas for one section. Let's do a couple examples. Finish up this section and finish up our afternoon. We'll start with y equals x cubed between 0 and 5. Now, they have to give you the function and the interval that you're going to look for the surface area on. So they have to give you both of these pieces of information. Now, based on these formulas, I already know that I'm going to need, and let's see, I can probably bring you back down a little bit. Sorry if you're getting vertigo here. I know I'm going to need the derivative on this, so let's just calculate that right away. Y prime is going to be 3x squared. All right, that's looking good. Let's plug everything into this formula, see if we can't find the surface area. So that's going to be the integral between 0 and 5. 2 pi, I wrote it in the integral, but you know what? That can come out because that isn't dependent on our variable. F of x, that was our x cubed, and 1 plus f prime of x, which is 3x squared, squared again, dx. Well, let's take a look. Our integral can simplify a little bit. It's going to be 1 plus 9x to the 4th power dx. And that might be a little bit of a challenge here. How am I going to integrate that? Doesn't look like anything I know of. So I'm open to suggestions. What do you got? Any suggestions of how we can find an antiderivative here? Is this partial fractions? Is it integration by parts? Is it a U substitution? Is it, what other tricks do we learn? Is it trig substitution? What you got? Anyone?
Maybe a trig substitution because it's a constant plus the x, a variable. So I guess it would be like a tan.
It does look like a tan would work out pretty good. Kind Can I make a suggestion though? I would suggest that you try the easiest things first. Now, there's nothing that's going to simplify in the integrand itself. Then the next easiest thing would be a U substitution. And I guess what catches my attention is I got a 4th degree term here. What happens when you differentiate something of a 4th degree? What happens to the degree of your polynomial?
Down.
For a 4th degree polynomial,
2.
it's going to be a 3rd degree polynomial, right? It decreases by 1. So what's that suggesting? I hope it suggests a U substitution. Now we've learned a lot of cool techniques, but you don't get bonus points for solving this in a way that's harder than you need to. You just get full credit, which is fine, but if we let U equal 1 plus 9x to the 4th, and I did this in one of my other videos, I'll do it again here. Differentiate with respect to x, that's going to be 36x cubed. So du equals 36x cubed dx. And that's looking pretty interesting because I've got an x cubed dx in my integrand. So all that's left to do then would be to rewrite that as 1 over 36 du is equivalent to x cubed dx. And now I can interchange these things. This is as good as this. So I can make a substitution. There's probably one more thing I should do before I do my substitution. Does anyone see what that would be? I mean, I guess you don't need to, but I would change the limits. So I have u of 0 and u of 5. I think 5 is going to be a whopper. Let me take a look here. So u of 0, well, that's just going to be 1. So that's good. U of 5, whoo, man. Let's see, 5 to the 5th power, 5 to the 4th power is what, 625 times 9, what, 5,600 and something? Wow. 5625, let's see. 9 times 625. Yeah, I was right. Plus 1, there you go. 5626. That's a big one. 5626. But that's okay, because we don't have to change our limits back. We don't have to go back. We're just done with x's because we've changed our limits. So let's finish this off. That's going to be 2 pi times the integral from 1 to 5626 of the square root of u times 136 du. So kind of a lot going on there. That's okay. Let's take a look here. I'd probably rewrite that. I'd take the 136 out in front, 2 pi over 36, and I know that reduces to 1/18. 1 to 5626 of u to the 1/2 du. Well, let's keep going. We can find the antiderivative of that. Let me cancel that out and write that as pi over 18 times u to the 3/2 divided by 3/2 between 1 and 5626. 3/2 times 18 is going to give me 27. So this becomes pi over 27. Let's do it this way. I don't want to do too many steps at one time. between 1 and 56/26 of u to the 3 halves. Now I'll accept the answer that I'm going to show you here. I think the book is going to write it a little bit differently. Plugging in the upper limit, it's going to be 56/26 to the 3 halves minus 1 to the 3 halves. And of course, 1 to any power is just 1. This is fine. Nothing wrong with this. Just kind of an FYI, u to the 3 halves is really u to the first power times u to the 1/2. So another way you could write that is u times the square root of u. And with that in mind, you could write this as 56/26 times the square root of 56/26. And I think that's the way the book wrote it, but you know what? There's nothing wrong with that. This is just showing off with some algebra skills. So I'll be happy with that. Completely happy with that. You get here, and 2 of us will be happy. Okay, looking good, looking good. How's that first one? Anything special there that you'd like me to go over a little bit more? Now, again, these are just a couple formulas, and beyond dealing with the integration issues, it's plug and chug. Just that simple. Yeah, please. Is there a question I can help out with? One more time, question out there? All right. So just kind of a recap here. Found the derivative, squared the derivative. We got this function. You know, trig substitution might work, but if there's something simpler that works, like just a regular old u substitution, hey, go for the u substitution. All right. And the u substitution here worked out pretty nice. Gave us this. Kind of a large number up here, but that's okay. Still the right answer. After our u substitution, found the antiderivative, plugged the limits. Again, this is fine for a final answer. Nothing wrong. If WebAssign marks that wrong, you tell me. I want to know. That shouldn't be wrong. Let's do another one. Y equals 1/3 x to the 3 halves. And that's 0 less than or equal to x less than or equal to 12. We're going to do this one around the y-axis. And the importance there is that it means you have to use a different formula. All right? In front of the integrand, you're going to have an x as opposed to an f of x. So let's rock and roll on this one. We'll start by calculating the derivative. Y prime is going to be 3 halves times 1/3 x to the 1/2. And we'll clean that up. That's just going to be 1/2 x to the 1/2. So a little bit of background noise, so I've muted you guys. But if you like to answer some of my questions, please do. Let's find the integral or the arc length. S is going to be the integral from 0 to 12 of 2 pi. And this time times an x. It's not f of x, it's just a simple x times the square root of 1 plus f prime squared, 1 over 2 times x to the 1/2 squared dx. The 2 pi can come out in front. 0 to 12 x square root of 1 plus 1/2 squared is 1/4. X to the 1/2 squared is just x dx. Okay, so we're kind of stuck a little bit here because we don't have something that's going to work out pretty nice here. So a lot of the things that we do in section 8.2 and 8.1 really are giving me a chance to emphasize some of the things we did in other sections. And one of those things that we did was kind of a fancy U substitution. If this was just U to some power, I'd be okay. It's not quite what I've got. So let me do this. Let's let U equal 1 plus 1/4 x. And that means the derivative du by dx is just going to be 1/4, or better yet, du equals 1/4 dx. Okay. Now I don't have a 1/4 in this, but I do have a dx. So if I multiply both sides by 4, I get 4 du equals dx. I'm also going to take the time to change my limits of integration. U of 0 is going to be 1 plus 1/4 times 0. So it's going to be 1. And then we're going to have U of 12, which is going to be 1 plus 1/4 of 12. 1/4 of 12 is 3, plus 1 is 4. So cool. So I can change my limits of integration, but I'm going to run into a little bit of a problem, at least for the moment. It's not a 0 anymore, it's a 1. One to 4. The square root of u, dx was 4 du. What am I going to put in for x? How am I going to get x there?
Could you solve the u equation?
Perfect. Absolutely perfect. Thank you. We can solve here for x. So if I move the 1 to the other side, I get, let's do it down here. U minus 1 equals 1/4 x. And then if I multiply both sides by 4, I get 4 times u minus 1 equals x. So absolutely perfect. That's exactly what we need to put in here, is 4 times u minus 1 times the square root of u times 4 times du. So the 4 times the 4 is 16 times the 2. I can put that all out in front. 32 pi, integral from 1 to 4 of u minus 1 times the square root of u, which I'll write as u to the 1/2 du. Now you might look at that and go, well, really? We did all that in we get nothing out of it, right? I mean, it's still a bit of a mess. But the big thing is we've taken this from 2 terms down to 1 term. And I can distribute that 1 term and then integrate both of these. So that's the big thing, is I compressed that term here, and that's what's going to allow me to finish solving. So it's going to be 32 pi times the integral from 1 to 4 of u to the, well, let's add the exponents, u to the 3/2 minus u to the 1/2 du. And these are terms that we can integrate. You've been doing that since Calc 1. So 32 pi, 1 to 4. And again, it's going to depend on you. I mean, if you're good at these things, do everything. If you struggle, and I saw some people making mistakes with these exponents on the exam, add 1 to the exponent is 5/2, and then divide by that same exponent. Add 1 to the exponent, 3/2, divide by the same exponent. Nothing wrong with taking a little bit of extra time with your antiderivative, and then maybe simplify. So 32 pi, 1 to 4, 2/5 u to the 5/2. Most of you probably will get pretty good at this, doing that in your head, jumping from here to here. That's great. Let's plug in our limits. 32 pi times, that'd be 2/5 of 4 to the 5/2. 2/5, 4 to the 5/2 minus 2/3, 4 to the 3/2. And at our lower limits, plugging in a 1 here is just going to be 2/5 minus 2/3. All right. So 4 to the 5/2, that's going to be 2 to the 3rd. That's going to be 32 times that. It's going to be 65/5 minus what? 16/3. Tell you what, let's just finish this off with our graphing calculator. So 2/5 is 0.4. 0.4 times 4 raised to the 2.5 minus 2 times 4 raised to the 1.5. Exit the exponent, divided by 3, minus parentheses 2/5, which is 0.4, minus 2 divided by 3. So I'm getting 7.7333333. Let's change that. That's something over 15, I think. Math. 116 over 15. Let's not forget there's a 32 out there. 3712 over 15 times pi. Beautiful. Okay. Thoughts on that one?
I don't really understand what we're accomplishing. Like, what does this number mean for us?
So, what you're finding is the surface area of a solid of revolution. So, let's think of Let's think of this curve right here. Basically a semicircle, right? Now, if I took this shape and revolved it around the x-axis, what shape or what volume is going to appear out of this?
Are we getting like the surface area of a sphere?
Yeah, well, it'd be a sphere, and this calculation would be the surface area of that sphere, all right? Which for a circle like this or a semicircle, you should end up with S equals 4 pi r squared would be the surface area. If you ran through the surface area calculations with this function, y equals the square root of r squared minus x squared, you should end up with this. I think it might be one of the problems in the book or on WebAssign for you guys. I'm not sure, but that's going to be what you're going to get. Now we're doing that same thing for different functions. Now, 1/3 x to the 3/2, that's going to be a kind of a little funkier different function, but you're still going to achieve the same thing. You're going to take some curve that looks probably something like this somehow, between 0 and 12. You're going to rotate it around the axis. It's going to look kind of like a horn or a bugle, you know, the end of a French horn or the end of a bugle, that spout that really opens up wide. And you're going to find the surface area of that region. So that's what this is all about. In fact, kind of building on that a little bit, let me leave you with this final paradox, just to kind of mess with your mind for a little bit. So it's a problem called Gabriel's horn. You're going to take a look at the volume of a solid of revolution of this function, y equals 1 over x, between 1 and infinity. Now, you have to pardon me a little bit. I didn't draw this all the way out to infinity because I didn't have that much time, but it's going to go all the way out to infinity. If you rotate this around the x-axis, you're going to get some kind of a horn, all right? Kind of maybe a bugle shape or something like that. And what I did here is I calculated the volume of that solid of revolution. It's a disk method because this is flush with your axis of rotation. So I found the volume of one disk. And you know what? It's an improper integral. But hey, we can deal with that. We did that in section 7.8. And I take the pi out, take the limits, and I end up with a finite volume of pi. So I could fill this up with pi cubic units of fluid or paint, if you wanted to think of painting this. Now that's the volume. Here's where it gets interesting though. If you wanted to calculate the surface area, so this is how much paint you'd have to fill up the volume with. But if you calculated the surface area, okay, so it'd be this type of equation, and you fill in the relevant information. All right, the 2 pi is out here. You get this, and you take your g squared, or y prime, and square it. If you get common denominators and play around a little bit, you get this. So we have to integrate this. But rather than bother you with all that, let me just note for you that this function, square root of x to the 4th plus 1, has to be bigger than this. So whatever this integral is, it's bigger than this, bigger than x squared here. But x squared over x cubed is going to cancel and give me 1 over x. And we saw earlier that this integral diverges. And what that's saying is that while the surface area is finite, or excuse me, the volume is finite, I could fill this up with, you know, pi gallons of paint or pi cubic units of paint. I can't paint the outside. It would take an infinite amount of paint to paint the outside. So it's a paradox. It's just something that, you know, doesn't seem right. And on that note, I will leave you. So enjoy thinking about Gabriel's paradox, Gabriel's horns paradox over the weekend, or actually over the next 2 days, because I'll see you Wednesday. But that's all we got for section 8.2. Not a whole lot that is there other than just some tricks of integration. So cool. Let me stop things here.